Hi, so this is Group 2B with our article translation assignment 1.2 with me, Nolan, and then we got Braden and Mason as well. And today in this podcast, we're covering an article titled Artificial Intelligence Computing at the Quantum Level. And forgive me for the pronunciation of these names, but it's by Olawale Ayoade, Pablo Rivas, and Javier Orduz. And yeah, Braden, you want to get us started with the article?
All right, yeah. So to understand what quantum computing is, first you need to understand the first word, quantum. Now, there's a few things we need to understand. First off is the idea of superposition. Now, I'm sure you've all heard of Schrodinger's cat. The general concept is a cat is stuck in a box and it has a certain probability of either dying or living. And before you were able to I mean the cat is in the box, so you can't see what happens. And by the time before you open up the box, the cat is in a superposition of two states. It is both dead and alive at the exact same time. But once you open up the box, that state collapses and it is either dead or alive instead of both dead and alive. But how does that correlate to quantum computing? Well, particles are the same way. Particles can be in a superposition. And when you observe the particle by measuring some values of the particle, that superposition collapses and the particle changes its state. All right, so the idea of a cat being both dead and alive at the same time is already a pretty wild concept. But what if I told you it gets crazier? Let's say you have two cats in two boxes. What if I told you the state of one cat depends on the state of another cat? So if one of the cats in one of the boxes dies, the other cat in the other box will also die. And likewise, if one of them lives, the other one will also live. That is the idea of quantum entanglement. In terms of particles, a particle's superposition depends on another particle's superposition no matter where that particle is. That is what it means for those particles to be entangled.
Okay, yeah, it's a good breakdown of that. Those are, as far as I know, those are like the two like big main ideas of like quantum computing and how like it interacts or like quantum computing interacts with the ideas of quantum physics, being the ideas of like superposition and entanglement. So thank you for giving a good intro on that. And another thing as well that the article makes sure to cover is the idea of like quantum machine learning. Now, machine learning in general is the idea of like feeding a machine information and then letting that machine learn on its own like a human would. If you were to give a human like a book, they could read that book and learn the contents of the book. Machine learning follows the same principles. Whereas, but in quantum machine learning, which is one of the main focuses of this article, that and it's brought up in the introduction here, is that quantum computing blends different quantum algorithms using the quantum properties that Braden mentioned beforehand, and it uses those in order to influence how machines learn different subjects. And it, in this case, or in these cases, ideally, it improves the machine learning process that makes things more sophisticated. So, in overall, these are probably the two main focuses of this article and like what the researchers are trying to find, which is I think is important. But from here we will move on to explaining some more general topics so that people can get a better idea. So to get in, like with what a quantum computer is, much like a normal computer, it is something that is used in order to do computations, but it works similarly but differently than normal computer at the same time. They follow the same somewhat principles but act on these principles differently. Probably the biggest difference to start off is the idea of what a bit is versus what a qubit is. Now, a bit in normal computing is the smallest form of data that can be stored. And with a bit, it's either 1 or 0, like on or off, true or false, one of those scenarios. Whereas with a qubit, it acts like a qubit can act as a superposition, much like Braden mentioned earlier with Schrodinger's cat example. And with this qubit being able to act as more than just 1 and 0 at the same time, and then sets of qubits acting on each other through entanglement, which is what Braden also mentioned. Quantum computers are able to perform more complex and like more difficult computations in comparison to a normal computer, and it can do them faster as well. Now, how it does this is through things known as logic gates, and these gates take in signals and give certain outputs depending on the input signals that it gets. For example, in a normal computer, there's a thing called an AND gate, and with this gate, it takes in two signals, and as the name suggests, you need the first signal and the second signal in order to get an output. Now, in quantum computing, these gates work much the same way, but there's different quantum mechanics focuses on certain gates that give specific outputs. And the quantum computer uses these specific outputs that only a quantum gate can produce in order to be what a quantum computer is, in order to allow for faster computations, more complex computations, and yeah. Is there anything that you two can think of to add? Because I'm drawing a blank.
I just like how quantum gates work, like how similar a quantum computer is to a normal computer, but how different it is at the same time.
Yeah, exactly.
Like a normal
Right.
computer works with the bit system, which is already pretty sophisticated. Like it's an extremely small system by only using one operator, but having two possible values, so it exponentially grows.
Yeah.
But instead with a qubit,
It grows even more exponentially, right? It's just,
yeah.
and it just opens up a whole new world of possibilities in the world of in the world of quantum computing, right? And that
Hmm.
makes things obviously better. Unfortunately, though, there are some downsides, and I think we're gonna we'll get into that a little bit later. But now let's talk about some of the different uses that we have for quantum computing, or the uses that we have right now, and future uses that we think we can use for these.
But another application of quantum computing is the idea of quantum encrypting. So with classical encrypting, uh, it's already still a really clever system. They use um, two large prime numbers multiplied together, and a classical computer, it takes years upon years to encrypt that. But with the presence of quantum computers, they're able to decrypt that almost instantly. And so we need another type of encryption system, and that's where quantum encrypting comes in. Similarly to normal encrypting, the sender will send a key to the receiver, and with the receiver, they are able to use this key to decrypt the data. But in terms of quantum computing, instead, the sender will just send a key that's made up of particles. And when the receiver receives the particles, they're able to have the key to decrypt the data that's sent to them. But the really interesting thing about this is that in classical encryption, an outside observer is able to read the key that's sent from the receiver and the sender. But with quantum computing, the idea of superposition comes into play. Because when you analyze Schrodinger's cat, it collapses the superposition and turns the cat into either dead or alive. And so when the photon or the particles are read by the outside observer, the state of the particles will change, and so the key will become completely unusable. And that's why quantum encrypting is virtually undecryptable and takes it's just essentially impossible to decrypt.
With what we know so far.
Yeah. I mean, the important thing about this.
If it becomes normal, people are gonna figure out how to break it. But like, you know what? What are you gonna do, right?
Mm-hmm. And I mean, the field is always progressing, so we don't know where it's going to go.
Like, I think the important thing to note is that like with the encryption part, the keys they essentially work as like passwords, right? Yeah.
Mm-hmm.
And with quantum computing, think of like the longest and most intricate password you can think of. No one's going to be able to guess it on the first try, right? And
Yeah.
more than likely, no one's ever going to be able to guess it. And that's sort of the idea behind it. One might think, when can I get a quantum computer in my home? You can't, you probably won't ever, which is unfortunate. Sure, many people would like it considering how much faster they could be. But as of right now, there are many, many drawbacks with quantum computing. One of the biggest ones, and the main one that's discussed in our article, is that there's nothing a quantum compute there's nothing that a quantum computer can do that a traditional computer cannot. And this comes in the fact that a lot of the time the algorithms that a quantum computer runs don't exactly always work out faster than the way that a normal computer could run it. Now, this doesn't exactly have to do with just the algorithm itself. Like a quantum algorithm is much faster than a normal conventional algorithm. But the problem is converting data from like a classical computer to data that can be used on a quantum computer. And with this data, it takes so much time to convert between the two that at that point the overall time that it would take the quantum computer to run something, it just you'd be better off just using a normal computer, which is unfortunate. Fortunately, though, we're getting to the point where theoretical ideas are being like come up with that can potentially be put into place in order to make make this data transfer faster, which in the future, if this comes to be, it would be very beneficial and allow us to make huge strides in the world of quantum computing, as time that it takes to convert the data is probably the biggest limitation we have right now, other than some of the theoretical and experimental limitations that can be found, as we still don't entirely understand everything.
So, like AI, the two English vocabulary refer to like artificial intelligence, and you can think as AI as different different workers. Like it can be designer, like a developer, or assistant, analytics, or something. Yeah, because AI is a like a virtual person that you can help you do anything you want and solve a lot of problems you have difficulties. And there's only two things you need to have to create an AI, which first is the tools to write the AI, and second is the environment to create the AI. So if you have the environment to write the code, then your tools will be like keyboard and your brain and your way of thinking to create the AI. So so AI it could like enable people to create innovative solutions, and also it could help people to create new ideas and also improve a company's product. And so also that it can help people to stay competitive in lots of job market, for example, like tech industry, or also like finance industry. Like because AI could make people make your ability to deal with a lot of problem uh to reduce the time you deal with a lot of problems. So AI is a like a virtual person that know a lot of things. So for human people, you just need to input lots of data into this virtual person's brain. Then you can create and help you deal with a lot of problems and make a lot of solutions you can't think about.
How does quantum computing affect AI?
So um, I think it will be more but it will be better to say AI like like put into quantum computing, because um if you have the AI in the quantum computing, it can first like it will uh improve the error corrections, which can advance machine learning algorithm, and it could predict when errors are likely to occur and take corrective action in real time. So you will improve lot of error when you are doing your task, you or like complex problem. So this is the first things that AI will be uh, improve in the quantum computing, and second will be the problem solving. So if you have the AI in your quantum computing, it could help to identify which problems are best suit for quantum computing, and how to structure these problems for a quantum algorithm most effectively. So some problems might be solved most efficiently using the combination of classical and quantum computing. But if you have the AI, it could manage how tasks are allocated between these systems. So this is the 2 point. I think AI could improve the quantum computing. Yep.
Yeah. And one thing I'd like to add as well, just for like how quantum computing can help AI rather than the other way around, considering that's what our article is more focused on, is the fact of like what machine learning and specifically quantum machine learning means for quantum artificial intelligence. And as we look into it right now, artificial intelligence is highly powered by machine learning and information that machines can intake and learn from, and then the AI views this information and uses machine learning to become more sophisticated. And as quantum computing is already so much more sophisticated than classical computing is, and it follows that quantum machine learning leads to more sophisticated AI. Am I right in saying that, Mason?
Yeah, that's true.
Yeah. Okay. Sounds good. I just wanted to clarify that. Fortunately, our article, even though it was titled with artificial intelligence, it didn't talk much about it. So we still felt it was important to bring it up. But yeah, unfortunately, that's about all we can pull out from that, unfortunately. Should probably add that, like, our article, unfortunately, isn't an IMRAD article, so the research process isn't the same as what it would be for an IMRAD article. Instead, ours is a review article, so the researchers took in information from other articles and created their own that kind of reviewed all the information. But that's okay. Covered the topic, and I think we did a pretty good job.